Hey, this is Luke. I'm going to do my my presentation on Vulkan. There is a huge amount to cover, and I can't really do more than scratch the surface. So I just wanted to show you kind of a couple of key features and to give you a bit of a general sense of kind of how it's structured and used. So the first question is, why use Vulkan over OpenGL, and kind of what's the difference between the two? And really, Vulkan is just about having tighter control over what you're doing to allow for performance gains in terms of how we're utilizing the GPU and interacting with the GPU, and also harnessing modern architecture a bit better than OpenGL does. This means we have less reliance on drivers, and some people kind of joke that it's, well, maybe not joke, but say that it's kind of half graphics API, half GPU API, because really what you're doing is kind of removing a lot of what drivers traditionally did, which is kind of provide this sort of middle layer of interpreting what you're doing, passing that onto the GPU, and sometimes that wasn't as efficient as people wanted. And also doing some asynchronous CPU operations. So we parallelize things on the GPU, but on the CPU side, we're not necessarily using it as effectively as we can. But Vulkan, actually, you can make use of that by using multiple threads to do things like generate command buffers and sort of queue them up for submission to the GPU, and we'll talk about that a little bit. Also, a lot of memory management is actually left up to you as the developer when allocating command buffers through command pools and things like that. And one more feature is just that it's a unified API across platforms, which is nice. And here's just a quick little visual demonstration. Obviously, the first thing that comes to mind, that comes to your eye, is just a sort of thinner layer of drivers and kind of middleware between the application and the GPU. So you're doing a lot more. And so that layered architecture about debugging and validation, I'll talk about as well. And the runtime API only has to ingest Sphere via intermediate language, and I'll get to that next. So basically, this is just sort of a bytecode format for shader data. So right now what we do is we will write our GLSL for our applications, and we will submit that, and that will get compiled on the GPU, and then we will use that for our shaders and things like that. But one of the problems is that from GPU to GPU and from driver to driver, these languages can be interpreted differently and can have errors and issues, and there can be some costs associated with creating those shaders as we're running our application. This just makes things a bit faster, and also kind of provides a uniform target for us to use when we're kind of using those shaders. So that's nice. And here's just kind of another good image which gives you a little bit of a sense of how this helps. So you can have, and actually, in terms of generating that, you can use higher level languages, and then you can precompile into this format, and then that's what you're going to be translating and submitting to your graphics card here. And this can allow other vendors to develop compilers and use different languages, and the result is going to be the same, and GPUs should be able to interpret that. So in terms of kind of how Vulkan applications are set up, there's a couple of important concepts for kind of managing the application. So before I even get to these devices, one thing to mention is instance. So we create a Vulkan instance, which kind of is our way of communicating between the library and our application. So our instance will create it with some parameters related to the API version and sort of some settings that we want to have. And then once we have the instance set up, we're going to create our devices. And the first thing we're going to do is create a physical device. And this literally is corresponding to our actual hardware. So whatever GPU you've got in your machine, that's what we're talking to. So if, for me, if I'll create a physical device, it will find the graphics cards on my computer and list them, and you can see their properties. So it'll be NVIDIA, GeForce something, and some properties about that. So when you use enumerate physical devices, that will grab us a list of possible devices. And additional information might be, what vendor it is, what's the driver and version info. And then once we have our physical device, we want to create our logical device, which is kind of going to be our handle for using this physical device and harnessing it for our operations. And so the logical device just provides us a nice view and API for talking to the GPU. And that logical device is going to be used throughout the application for creating and managing command pools and buffers and kind of shuttling data back and forth, which is going to do using queues and queue families, which I'll talk about as well. So queues are kind of how we submit commands to the GPU and perform operations. Unlike other APIs where you'll call a function like GL something and it will immediately carry that operation out, that's not really how Vulkan works. What Vulkan will do is it will take that call and it will submit your commands to a particular queue and queue them up for passing them to the GPU. So what you'll do is you'll create your commands in what are called command buffers. You'll take all the operations that you want to perform, wrap them up, and you'll submit the command buffer. And when it's time, it will pass on to the GPU. They will be done. So these command buffers will be kind of passed along in the order that they're received on a per queue basis. So if you have multiple queues, there's no guarantee of ordering between them. But within a single queue, it will go in that order. And you can actually synchronize multiple queues with some various some tools like semaphores. So queues can belong to different queue families, which perform different operations. So you might have queue families which do operations related to actually rendering graphics or compute shaders, or you might have another one which is just for passing raw data onto the GPU. And even though they might do different functions, you can also one queue isn't necessarily one queue family isn't necessarily tied to one specific operation. So, for instance, a single queue family can handle both graphics and compute, and passing along raw data to the GPU, and then maybe not do some other operations. I guess if you have a more general purpose hardware, then it will be able to do more of these at one time. So what are these command buffers I keep talking about? So drawing operations that we're going to be doing are going to be kind of packaged up into these command buffers. And what this allows us to do is prepare these commands in advance. So in multiple threads, we can create multiple command buffers, each of which have their various operations packaged up into them. And then when we're kind of looping through, all we have to do is just queue these things up and they're ready to go. And the cool thing about command buffers is that they're actually kind of modular. So you can have your primary command buffers, which are what's actually executed by a queue. And these just might have a list of operations in them that are just basic operations like command calls. Or you can have secondary command buffers, which can be called from primary command buffers. And these can kind of be reused. So you can think of it like routines and subroutines in order to reuse components and not write everything multiple times, which is really cool. So when you're creating a command buffer, what you'll do is it's called recording it. So you'll have command buffer start recording, and then you'll list the operations that you want to be part of it, and you'll be referencing the specific command buffer. and then once you're done, you'll hit end command buffer, and then you're done with that. So you might loop through various operations with various different settings, things like that, and then you'll have a nice collection that you can use. And command pools just manage the memory associated with command buffers. So we're going to allocate, every time we create a new command buffer, we're going to specify a command pool that we're getting that memory from. And a command pool is associated with just one type of device queue. So you can only create command buffers related to that that type. And so when you execute those particular command buffers, they kind of have a single queue that they're associated with. And they're not just being sort of like spread out over random queues, so you have control of kind of where these different operations are routed. Another interesting thing is these preset graphics pipelines. So the way I understand this is that it's not quite like OpenGL, where we're just like setting shaders to context and specifying, and then making these draw calls based on that. And it seems like Vulkan just has completely distinct rendering pipelines, which are actually objects, and these are specified ahead of time in order to kind of improve performance. I guess it's because we're not. I guess it's more predictable, the operations that we're doing. So I guess there's probably some hardware considerations and cache considerations when we're performing these operations. So, but it doesn't mean you have to set up multiple of these pipeline objects ahead of time, and you're just going to swap between these complete sort of sets of features. Validation layers are, as we saw in the graphic earlier, they're not actually really debugging and validation isn't really baked into the raw API. What it does is sort of allow for you to determine what and how much debugging you want to include in your application. And this kind of goes back to the idea of modularity, which is kind of a recurring theme in Vulkan. So you can kind of snap on these different components and examine different parts of your application and see sort of what's wrong, and then when you want to release or you need performance, you can just disable those layers pretty quickly. And here's just a couple of examples of those validation layers. So you can see we've got validation related to API calls. We're looking at object tracking and memory leaks within our application. We can make sure that some of the resources that we're using are valid, and that we're not kind of going over any sort of boundaries here. Looking at threading, so it's pretty cool. And so just in terms of kind of to give you a bit of a higher level look at some of the operations that we have to perform in when we want to actually get something shown on the screen. So first we'll create our instance, which has our API and version information, and use that when creating our physical device, which is our actual GPU hardware. Then we'll create our logical device, which is related to the physical device as our kind of handle. And as we're creating the logical device, we're also specifying our queue families and format and number of queues that we're going to be using. Then we do some familiar operations like setting up windowing, and you can still use third-party libraries like GLFW for these operations, and set up the swap chain, which we know, and set up render targets. And after that, we create image views and frame buffers and render passes. So these are kind of similar concepts to what we've seen before. A lot of this is just kind of specifying what image in the swap chain that we want to be rendering to. Render passes can describe some additional options when depth stenciling when we're preparing our target as well. We create the graphics pipeline, which is our rigid graphics pipeline using some of these components that we've set up as we get ready to start, and then we'll create our command pools, from which our command pool is based on different types of queues, and within those command pools creating different buffers which have various commands. So a command buffer that we use for kind of the drawing stage is we'll start our render pass, we'll pick the rendering pipeline that we want to use for this pass, actually perform drawing vertices, and end the render pass. And all those operations, those commands, are going to be wrapped up into a single command buffer that's going to be submitted, and then that can be submitted multiple times as we're looping through our program here. And then we've got the main loop. So there's more resources than I can list. I didn't even want to try and get all of them, but this I thought isn't really as much of a technical deep dive as it is just a really good look at kind of where Vulkan API actually sort of came from, and its kind of its history. So kind of looking at some of the motivations and sort of decisions that led to Vulkan as it is today. So I thought that was really cool, and I'd recommend checking out that article. I think that's all that I wanted to go over. There's a ton more, and I would definitely recommend looking into this because it's actually really interesting, and from all the code samples and things that I saw, it seemed to be parts of it are more approachable than I was expecting, and it's very sort of like explicit in the way that it's typed. So yeah, give it a shot. Thanks.